Try one more example here. The sum of 1 minus 2 over n raised to the n squared power. Now, what I notice right away about this one is that I have some stuff involving n, that 1 minus 2 over n, raised to some stuff involving n in the exponent. So I have n both in the base and the exponent. That is not something I want to use the ratio test. Don't use the ratio test for something like that. Instead, you want to use the root test for something like that. When you have something involving n raised to something with n in the exponent, you want to use the root test on that. So let's try this out using the root test. Remember, that says you look at the absolute value of an raised to the 1 over n power. That's the nth root of the terms. So this is 1 minus 2 over n raised to the n squared, all raised to the 1 over n power. Now I'm going to get rid of the absolute values right away because 1 minus 2 over n is, after n gets to be big enough, that's going to be a positive number. So this is 1 minus 2 over n. Now n squared raised to the 1 over n is, remember, you multiply those exponents. So that is n squared over n, that's just n. Now this is a tricky expression, 1 minus 2 over n to the n. And we've seen an example like this before in another lecture. The trick here is when you have something complicated raised to a complicated exponent, you try to separate them out. You write this as e raised to the natural log of a to the b. And then the point of doing that is that you can pull the exponent b out of the natural log, so you can write it as e to the b natural log of a. So here, the a is the 1 minus 2 over n, and the b is n. So we can write this as e to the n times the natural log of 1 minus 2 over n. And now we're just going to focus on the exponent because that'll take a little work to sort out. We'll come back later and incorporate the e term. Let's just look at that exponent. N times natural log of 1 minus 2 over n. N times natural log of 1 minus 2 over n. Well, n goes to infinity. Natural log of 1 minus 2 over n. Well, 2 over n goes to 0. So that's natural log of 1, which is 0. So we've got an infinity times 0 situation. Now, you can't do anything with infinity times 0. It could come out to be anything. What I mean is you can't do anything directly. What you can do is write it as, well, you can write it as natural log of 1 minus 2 over n divided by 1 over n. And so that's going to, the numerator is still 0. 1 over n is now 0. That's going to 0 over 0. And that's a situation where you can use L'Hopital's rule. So we're going to invoke L'Hopital's rule here. Remember, with L'Hopital's rule, you take the derivative of the top and the bottom separately. It's not like the quotient rule from Calculus 1. It's kind of different. You take the derivative of the top and bottom separately. I'm going to take the derivative of the bottom first because it's easier. Derivative of 1 over n is negative 1 over n squared. Now, the derivative of the top, natural log of something, is 1 over that something, 1 minus 2 over n, times the derivative of the inside part. So that's the derivative of 1 minus 2 over n is minus 2 over n squared, and the negative of that turns that into a positive because the derivative of 2 over n is negative 2 over n squared. The derivative of negative 2 over n is positive 2 over n squared. So let's clean this up a little. The 1 over n squared cancels away with that 1 over n squared. and we're left with negative from the denominator 2 over 1 minus 2 over n. And now as n goes to infinity, the 2 over n goes to 0. This whole thing goes to negative 2. But remember, this was the exponent. So if we incorporate back in this e that we had before, the true limit here, an to the 1 over n, goes to e to the negative 2. So our limit L that we check for the root test is e to the negative 2. That's the same as 1 over e to the 2. Now we have to figure out approximately how big that is. E is about 2.7. So 1 over e squared, I don't know exactly what it is, but I know for sure it's definitely less than 1. And that was the cutoff for the root test. So if L is less than 1, that tells us that the series AN is absolutely convergent by the root test. So let's recap what we did here. The first thing we did when we looked at this series is to say, I see an n in the base and an n in the exponent. That's something complicated, not something that the ratio test is going to work well on. So that tells me right away, try for the root test. So I set up an to the 1 over n. Now that simplifies down a little bit and we get to this step right here. And when we look at that step, again, looks like something a little complicated, so I can sort it out using this e to the natural log rule. You sort it out using this e to the natural log rule, and if you just look at the exponent, you get infinity times 0. Well, you can rewrite that as 0 divided by 0, which allows you to invoke L'Hopital's rule. You work L'Hopital's rule through, and you get negative 2. But that negative 2 is actually just the exponent because we still have this e from earlier. So we get e to the negative 2 as our final limit. And then the important thing about that was that it was less than 1. And the root test says if your limit is less than 1, then the whole series is absolutely convergent.